Welcome to our first lecture on this new series of lectures in general topology. Let me talk about the prerequisites before we proceed, because this is the first lecture, so it's a good idea to be sure as to what one needs to know. We will assume a solid background in real analysis. So one should be very clear about what are real numbers, what is the notion of convergence, what is the meaning of continuity of a function at a point of continuity of a function of this sort at a point, and in fact continuity of a function at any subset. S is a subset of reals and f is a function of this sort. What is meant by f being continuous at a point in the domain? These things we have discussed in a separate playlist on real analysis, and various things like open sets, closed sets, also the Heine-Borel theorem. So we'll assume that one is familiar with all of those things. Not that we will necessarily assume all the details. Some of the theorems we might end up reproving, but without the background in real analysis, it might be hard to appreciate a lot of things that we are doing. Okay, so a solid background in real analysis is important. Maybe one can skip the calculus part, meaning the part where we differentiate or integrate and all that stuff, but knowing that will only help. Okay, and we will assume some familiarity with linear algebra. The basics should be well understood, like what is a vector space, what is a linear map, what is a basis. Every finite dimensional vector space has a basis, the notion of dimension, linear functionals, dual spaces, space of linear maps, and inner products. Very important. We need to know what are inner products, and determinants. So a fair amount of linear algebra is assumed, but we will be only concerned with the real number field and the complex number field. We would not need to know the theorems or anything about arbitrary fields. Linear algebra as it pertains to arbitrary fields, that is not required. And a lot of structure theory of linear maps may also not be needed, like the notion of, if you followed my lecture series, we discussed something called eigenpolynomials and whatnot. Maybe all that is not needed. Eigenpolynomials, as we stated, was non-standard terminology, which I developed just for my purpose. Okay. And some basics of group theory, like what is a group and group actions. So if one is familiar with those things, like maybe we will not be using any finite group theory as far as I can tell right now. Not things like Lagrange theorem or Silo theorem. Those things are not needed. But a general familiarity with what is a group, the philosophy behind it, and things like group actions. So more or less that. And of course, if at some point one feels uncomfortable during the course of this lecture, if one feels uncomfortable about any particular concept, one can go back and learn them from various books or online or from my lecture series. In fact, that is how one learns mathematics anyway. One has to go back and relearn some things. When you relearn, you learn better. Okay, so much about prerequisites. And now let us start this lecture. The point of this lecture is to motivate the notion of a topological space, and we'll get to that. So first of all, what are the objects of interest? What are the things that we are going to study? So here, the first thing that I meant to draw was R2, right? The coordinate plane. The second thing is R3. And in real analysis, we study continuity of maps between real numbers. So the domain and the target of the function is typically the set of reals on both sides. Sometimes we can have a subset of the reals here also. So that is what we learn in real analysis. But clearly, there should be some notion of continuity that one can talk about on the coordinate plane also. At the very least, one should be able to imagine continuously moving on the coordinate plane. And also maybe you should be able to see that one can talk about functions from the coordinate plane to, let's say, the real numbers. And when can we call such a function continuous? There are ways to haphazardly map points on this on the coordinate plane to real numbers, of course, but there should be a notion of continuous map continuous map from the coordinate plane to real numbers. So we would like to formalize that notion, and one can do that in a somewhat ad hoc manner. Anyway, similarly, this is the three-dimensional vector, what should I say? This is R3, the three-dimensional real vector space. And surely there must be a notion of continuity here also. One should be able to move continuously here. One should be able to talk about a surface inside it and so on. And also continuous functions from here to, let's say, even the coordinate plane maybe, or better yet, to the three-dimensional space also, or to some other nice object. So the same questions or same notions should exist in this context. And here I meant to draw the unit circle. So there is nothing inside and nothing outside, only this ring. And again, this is a fairly nice object. One should be able to, for instance, walk continuously on it. And one should be able to talk about continuous functions from this ring to the real numbers. And here I have the hollow sphere, the kind of the two-dimensional version of the ring. So this is the hollow sphere, nothing outside and nothing inside, but there's this surface like a ping pong ball. And same questions, one should be able to walk continuously on it. One should be able to map it continuously to, let's say, the circle, or to the three-dimensional space, or to the coordinate plane, or to the real line. This is the torus, the cycle tire tube. If you've seen a cycle tire tube, that's what I meant to draw here. And if you've seen a donut, that is a solid version of it that is filled from the inside. Here I meant to draw empty inside, empty outside, but only the surface is there. Same things. This is a fairly nice object. One should be able to walk continuously on it, and so on and so on. Here I meant to draw a solid square. So this is a square, but it is filled from the inside. Now this is a little less nicer than the objects that we have seen so far, because here we have pointy corners, but still it is a fairly nice object, so that we should be able to talk about continuity, right? Here I meant to draw a solid cube, or even a hollow cube, whichever you like. Empty inside, empty outside is the hollow cube. Filled inside is the solid cube, and same thing. This is a fairly nice object, should admit some notion of continuity. Now this object is in some sense less nicer than the previous ones, whatever that means. This is a graph. There are these vertices, and then there are connections between the vertices. This is a graph, and again, there should be some way, and maybe it is a little less obvious in this example, but there must be some way of going continuously from one vertex to another while respecting the edges, and there should be some way to map it continuously somewhere. Okay. And this last one is absolutely unclear. What is this doing in this jumble of things? And what I meant was, as you keep bifurcating, you will see some horrible thing at the end. And it turns out that whatever notion of, whatever object general definition that we will come up with, which will capture all of these in one fell swoop, also allows for some exotic things to creep in. And it's a great accident or great fortune that such objects do creep in. These are non-natural objects in the sense that if somebody asked me to talk about continuity, I would never think of such things. But it's the marvel of modern mathematics that unexpected things happen. If you come up with a good definition, it somehow pulls us or pulls in some mathematical objects which one would not even dream of before. So what I'm hinting at here is the Cantor set. We will discuss this in some detail later. And so this is a very high-level motivation for studying topology, that we can talk about continuity in a very robust manner. That is the point of general topology in some sense, to study continuity. General topology is the most robust study of the notion of continuity by my lights. So that's why we should study it. Continuity is a very fundamental notion, and general topology satisfactorily captures that concept. And now, with that preamble, let's see what is the general flavor of the kind of abstraction or formalism that we are going to develop. So before we get into that, let us recall what was the motivating idea behind the definition of continuity that we gave in our study of real analysis. So suppose we are given a function from the reals to the reals, and let's say x0 is a point in the domain. So x0 is here and image is fx0. And what was the idea behind calling f continuous at this point? We said f should map points which are sufficiently nearby to x0 to points which are nearby to the image, meaning fx0. Let me call this y0 for convenience. So we would like to say, or we said, that f should be continuous or should be called continuous at x0 if points which are sufficiently near x0 map to points which are near y0. And to be more precise, what that meant was, once you choose an epsilon is some number that one chooses, whichever one likes, it's just that it should be a positive real number, then that endows this point y0 with the notion of nearness. So the points which are at a distance of less than epsilon from y0 will be called near y0 under this choice of epsilon. And now points sufficiently near to x0, meaning there should be a delta such that whenever you choose points which are delta near to x0, meaning which are at a distance delta, at most delta or less than delta from x0, all of those points map inside this region. And this is basically an enunciation of the Epsilon-Delta property, right? So points sufficiently nearby to x0 should map to points near to y0. And therefore, if we want to generalize this, suppose we have just some set x and a set y and a function between them, and we have a point x0 here and the image of x0 is, let's say, y0. When would we like to say that this map is continuous? Well, we would like to say the same thing, that points which are sufficiently near to x0 map to points near y0. But we run into an obvious problem. What does it even mean to say points which are near to x0? Capital X is just a set. So there is no notion of nearness anywhere in this picture. And the main object of general topology, which is just called, the name for that object is a topology, is basically an attempt to capture this notion of nearness. It's a synthetic endowment. How shall I say it? It is a synthetic way to endow the set X with the notion of nearness. And let me show you what I'm trying to say. The things that I'm going to say now are not going to be completely clear in the first lecture, and that is okay. These philosophical points become clear after one sees the formalism, and the formalism becomes clear after one sees the motivation. So it's the chicken and egg problem, but it helps both ways. So here is the kind of thing that we would be doing in the next lecture. Here in this lecture, we'll only be motivating things, but in the next lecture, we'll be doing the formal things. So fix any set X, and when I say a set, I mean a non-empty set. We don't want to develop the theory of the empty set. So here I mean that let X be a non-empty set. And let's say we have a map from X to R. How do we even talk about the continuity of this map at a given point? Let's say at a point little x0 in the set capital X. So let's maybe draw something. This is the set X, and that is the set of real numbers. And we have this map S, which takes little x0 to the point fx0, which we may refer to as y0. Okay? So how are we going to talk about the continuity of this map F at the point x0? So we will endow the set X with a nearness structure. We will endow the set X with the notion of nearness. So here is an attempt, a very lame sounding attempt, but essentially this is what is going to happen. So let tau be a collection of subsets of X, and let's put at least some condition on this collection such that the union of the things in tau is the entirety of X. Let's just put that condition. So we have a collection of subsets of X whose union is all of X. So every point in the set X is in some element of tau. In what we learned in real analysis, all I'm saying is that tau be a cover of X. That's all that I'm saying. Okay, so now we can think of, or allow me to think of points in, or the elements of tau as things which capture nearness. So suppose I have a point in the set X, call it A, and I have an element of tau, call it maybe U, which contains A. So U in tau, and A is some element of the set X such that A is in U, as shown in the figure. Then you can think of U as a notion of nearness around the point A. So U is like delta. So if we were talking about real numbers and A was a point on reals, then the points which are delta close are the things which are in this interval. So once you choose an element of tau containing the point A, you can think of that as a notion of nearness around the point A. So when would we like to say that F is continuous at X0 with respect to this nearness structure? Let me refer to tau as a nearness structure on the set X. When would we say F is continuous at X with respect to this nearness structure? We would like to say that F is continuous at X0 with respect to tau again. Let me write it. If the mantra is the same, points which are sufficiently near to X0 map to points which are near Y0. If whenever epsilon is chosen, epsilon greater than 0 is chosen, meaning you choose a notion of nearness in the target, there are points which are sufficiently near to X0 such that all of these points map inside this interval, this epsilon length, or rather 2 epsilon length interval. So whenever epsilon greater than 0, there is something in tau, there is some U in tau, the property that all of U, first of all, it should contain the point X0, and all of U goes inside the interval of length epsilon around Y0. Well, not length epsilon, of length 2 epsilon. Let me write that again. So this is like your delta neighborhood of the point X0 in the context of real analysis. You choose a notion of nearness around the point Y0. This interval is a notion of nearness around the point Y0. Then there should be points which are sufficiently near to X0, meaning some element of tau, points which are sufficiently near to X0 is just an element of tau which contains X0. So whenever we choose an epsilon and consider this epsilon interval around the point Y0, there should be some element of tau which contains X0. All of this such that all of the points in this element of tau map inside this interval. So I hope you are able to see that this does generalize, in some sense, generalize the notion of continuity as we see in real analysis, where we have reals on both sides. And it turns out that this is too weak. The way we have, if this is all that we say about a nearness structure, we won't be able to develop any useful theory. we'll have to put some conditions, some more conditions on this nearness structure. Surprisingly, a very mild set of conditions suffice. It just works out, and it captures and generalizes what we learn in real analysis to great heights, to amazing, dizzying heights, and we end up developing a very robust and very easy theory of continuity without even having a notion of distance. Here, I mean, the way we will develop it, you will see that, I mean, it's not like the way I'm going to develop it is some new or anything. It's some 100 years old, more than that. What I mean is the way the theory works is that there is no notion of distance, or rather, even without a notion of distance, you can talk about continuity. In real analysis, that is not very, very clear because the real numbers come with an inbuilt notion of distance. Here, the notion of nearness will not have anything to do with distance, and that is a great relaxation, a very fruitful relaxation. If I were to think of a general notion of continuity, perhaps I would have gone via the route of distance, and there is one such route. We will get into those things. Those are a little bit more special than the general objects we will be discussing. Those are called metric spaces, and we will dedicate a lot of time on metric spaces also. This course will contain a course on metric spaces as part of it, but the more general object, which is that of a topological space, will not come up with a notion of distance at all. In fact, some of these spaces cannot be thought of as, or cannot be put into the setting of spaces with distances at all. They are just not distanceable. The technical term is metrizable. Anyway, I'm throwing around a lot of words which I have not defined because I can't define them in one lecture. And as I said, it is not important to understand everything at this point. A lot of these comments will be clear after some time when you've seen some formalism, then you come back to it, you think about it, you discuss with friends, and then slowly things become clear. Okay, so that is as much I want to say about it. As usual, like, comment, share, subscribe, and I will see you next time.